Okay, so this is part 2, finishing our walkthrough of basic chemistry. So today we're going to talk about valence electrons. So atoms have electrons, and those electrons are found in levels or shells. You may remember writing electron configurations in chemistry. In biology, we're only going to be concerned with the outermost shell, the valence electrons. And that's because what we are concerned with in biology is behavior of elements with other elements. How do they react? What kind of bonds do they form? And the only electrons that are going to be involved in that are going to be the valence electrons. So atoms usually want to have 8. Another thing you should know about electrons, valence electrons or any electrons, is that electrons do have the ability to absorb energy. And when they absorb energy, for example, sunlight hitting the leaf of a plant, the electrons in the chlorophyll, which is the pigment that can help with photosynthesis, those electrons literally get excited and they jump to higher energy levels. They absorb the sun's energy. And when they return to their normal level, they can pass that energy on. So this is something that's going to come up in future chapters. I just want you to be aware of it for now, that electrons can absorb energy and jump to higher levels, and then they can release that energy when they return. And electrons can actually absorb enough energy that they leave altogether, and they can be passed from one atom to another. So just a little notation for now. All right, so what we call an atom with a charge is an ion. Normally, the number of protons and electrons are equal to each other. So if I sketch over here this calcium is number 20. So a normal calcium atom, let's just say this is calcium 40, would have 20 protons, and 40 minus 20 would mean it would have 20 neutrons. And since we don't see any kind of charge here, we can also assume that it would have 20 electrons, because the protons and electrons cancel each other out. So if we were to see now this calcium with a +2 charge, the question is, does it have extra or missing electrons? Well, you must remember that electrons themselves are negative. So if it had extra electrons, it would have an overall negative charge. And in this case, because it has a positive charge, it doesn't mean +2 as in add 2, it means +2. It has a +2 charge. That means this must be missing 2 electrons. And that would mean, by the way, if we knew how many protons it had, that this would have 18 electrons. And we can try one more. Let's try oxygen with a -2 charge. So if oxygen is number 8, it has 8 protons. A -2 charge tells me it has 2 extra electrons, and therefore this oxygen would have 10 electrons. So this is something that you should be able to do on a test. And this last thing just gives you a couple of examples of ions. You don't have to know these examples, but just be aware that the reason we're going to be talking about ions is because they are super important in reactions that happen in your body, like muscle contractions, nerve impulses, water balance, blood pressure, all those sorts of things, maintaining homeostasis, involve ions. Okay. So when we talk about bonding, bonding has to do with reactions between multiple elements. And the definition of a compound is a chemical combination of 2 or more different elements. Keep in mind they have to be different elements. So if you were asked if this is a compound, yes, because it contains at least 2 different elements. But O2, for example, would not be a compound. It would be a molecule, technically. It would be called a diatom. They're called diatomic molecules. But if you were asked which of these are compounds, there must be at least 2 different elements, not multiples of the same element. And they're combined in specific proportions, and then they have certain properties. Now, what will determine what kind of bond will happen is what's called electronegativity. Electronegativity is how strongly an atom wants electrons. Not its own electrons, but how strong does it want other electrons. The higher the electronegativity, the more an atom really wants to steal electrons from something else. And the type of bond that's going to form is going to be based on the electronegativity difference between the 2 atoms involved. If their electronegativities are very much the same, it would be sort of like us getting into a tug-of-war, and if you're exactly as strong as I am, nobody's going to win. And in that case, those 2 atoms would probably share electrons. On the other hand, if I was going to get into a tug-of-war with an NFL player who's super strong, he's going to be much stronger than me. That would be like having a much higher electronegativity, and he would be able to basically yank the rope out of my hands. And that's what's basically going to happen in an ionic bond, is that something has a much higher electronegativity than something else, and it can actually completely steal electrons. All right, so 3 kinds of bonds. First, covalent bonds. Sometimes these are referred to as non-polar covalent bonds. That means the same thing, non-polar covalent bonds or just plain old covalent bonds, it's assumed. So this is when the electronegativities are similar, and what you'll see is, notice in the picture how the electrons are being shared by both. Covalent compounds are going to be really important in the next chapter because the things we're made of, not the ones involved in the chemical reactions in our body, but the ones that compose us, proteins and carbs and fats and our nucleic acids, are all covalent compounds. They form structures in our body. They're flexible. They have all kinds of important properties. And so we'll be talking about covalent compounds a lot in the next chapter. The second kind of bond, slightly different than covalent, is polar covalent bonds. Again, just covalent by itself could also be called nonpolar covalent. What happens in a nonpolar covalent bond is that the two things are sharing their electrons, but they're sharing unevenly because one of them has a higher electronegativity than the other, so it pulls harder. Water is a really good example of this, and we're going to talk more about water in the next section. But it's sort of like if I was going to share a candy bar with you. If I split it in half and we each ate half, that would be a covalent bond. If I broke off a quarter of the candy bar and gave it to you, I still shared with you, but I got most of the candy bar. And that's what's happening in a polar covalent bond. And in this case, with water, oxygen is the one that's more electronegative. So it ends up with, this little symbol means partial. It ends up with a slight or partial negative charge, meaning the electrons are sort of hanging around it more. And the hydrogens end up with, again, that symbol means partial, positive charges. The electrons are hanging around them less. But it's not an ionic bond because the oxygen hasn't completely stolen the electrons. You can just imagine that they're hanging around it more. This picture on the bottom left is supposed to be showing where it's more negative and where it's more positive, and they're showing that the electrons are hanging around the oxygen. Okay. The final type of bond is an ionic bond. So an ionic bond is where one has an extremely different electronegativity than the other, meaning one really wants electrons and the other one doesn't really want their electrons that much, and so it's really hard for the one to steal the electrons from the other. And when these tend to dissolve in water and form what are called ions, and I listed some here, you don't have to know them, but like sodium chloride, magnesium, calcium, potassium are all important ions that are in our body chemistry. So ionic bonds are important, particularly when they're dissolved in water in our bodies. So you should be able to do this on a test. All right, so first question, how many valence electrons does sodium have? All you got to do is look at literally the outer ring. That's your outer shell. So it has 1. My second question, how many electrons does chlorine have? 1, 2, 3, 4, 5, 6, 7. How many do they have once they react? Well, sodium gives 1 to chlorine, so this would be a very good example of an ionic bond. Notice they're not sharing. 1 gave it away. And sodium now has 8 because its outer shell is now the shell beneath. And chlorine also has 8. So you should be able to do something like this or answer multiple choice questions about something like this. Okay, now that was bonds within a molecule, but there are also attractions between molecules. And if you think about it, this is why liquids exist. For example, you have water, one water molecule, and another water molecule, and another water molecule. If nothing was attracting them, why would water be a liquid? Technically, these should just float away and be gases. And so what allows liquids and solids to be possible in covalent compounds has to do with attractions between them. So the first kind of attraction, and we really won't talk about this one much other than the definition, is called van der Waals forces, or London dispersion forces. Chemistry, they always call them dispersion forces, but in biology, they always call them van der Waals. I do not know why. So this has to do with electrons being unevenly distributed for split seconds. Electrons are always moving around. And what will happen is, at any particular moment, if this is an atom, imagine these dots are my electrons. I kind of imagine electrons being in the electron cloud and like evenly spread out. But the truth of the matter is, since they're always moving, there could be a split second where there's more electrons on one side than the other. And that would mean this slide would, for that split second, have a slightly positive charge, and this side would have a slightly negative charge. And then as soon as the electrons move, the charges would go away, and maybe there'd be a charge somewhere else on that atom as the electrons move around. These are really, really weak. In chemistry, there's some examples of where they actually make a difference, but the example in biology that every textbook uses and you should know is the gecko being able to stick to glass. It doesn't actually have glue on its pads of its feet. What it actually has are these microscopic fiber-like things, and those tips of those fibers, the uneven movement of electrons creates these little tiny partial charges that are attracted to the glass, and it's almost like static. And so a gecko can walk up glass or walk up a wall. They would have a much harder time walking up certain other things that wouldn't have attractions to them. So that's called van der Waals forces. And again, other than this one slide, you will probably never hear about these again. Much more important that you will hear about many times throughout the rest of the year are hydrogen bonds. So they're called hydrogen bonds, but we are still considering them attractions. And you'll notice they are represented by dotted lines. And here they are between water molecules. Technically, and I told people to add to their notes, it's the attraction of hydrogen. It's usually to one of three things: nitrogen, oxygen, or fluorine on another molecule. This is not a bond within. In other words, this bond right here connecting hydrogen to oxygen, that's a covalent bond. That's not a hydrogen bond. Technically, it's a polar covalent bond. But these dotted lines, and in DNA, these dotted lines, those are hydrogen bonds. Why are they important? They actually make water molecules stick together, and we're going to talk about that in our next section. They are what hold DNA together. The A to T and G to C, if you remember the bases of DNA hooking together, those are hydrogen bonds. That's why DNA can unzip very easily and be copied. These bonds also fold up proteins in your body into specific shapes for enzymes and things like that. So hydrogen bonds are going to come up multiple times as we progress.